In this presentation, I'll be explaining AC voltage controllers. It is actually AC to AC controller, and the control technique used is integral cycle control. Now let us see AC voltage controllers. AC voltage controller is an AC to AC converter that controls the RMS value of the AC voltage applied to an electrical load. That is, we have the input voltage is a fixed AC voltage, and this AC voltage controller produces a variable RMS value of the AC output voltage. Therefore, in this, input voltage has a fixed AC voltage and output voltage is a variable RMS voltage that is available. Now, there are applications where it is often required to control the value of an AC voltage applied to the electrical load. There are cases where we require a variable AC output voltage with a fixed AC output voltage. There we can use AC voltage controllers. Coming to the generalized power system, the power electronic system as such, here this is a generalized block diagram of a power electronic system, in which here this is a source and this is a load as such, can be considered as a motor, which is to mechanical load is being coupled here. And if the source is an AC voltage with a fixed AC voltage, and if the load is remaining is an AC motor, that demands a variable AC output voltage or as variable voltage at the input side, then the role of the power modulator is AC to AC converter. There we require AC voltage controllers. And as here we can see that the input is a fixed AC and output is a variable AC output voltage. That is, RMS value of the output voltage is varying. And that is where there we use AC controllers, so AC voltage controllers. Another one is that cycloconverter that will be explained in another presentation. However, in this presentation, we'll be concentrating AC voltage controllers, in which the input is a fixed AC voltage and output is a variable AC voltage. Therefore, the RMS value of the output voltage can be varied. Now, continuing the AC voltage controllers, the AC voltage controllers can be also classified into two types based on the number of input phases. There can be either single phase AC voltage controller, a three-phase AC voltage controller. Therefore, if this is a topology of a single phase AC voltage controller, in which this is a single phase input and this is a load is there, and this is a back-to-back connected thyristors T1 and T2 are there. And here, by controlling the firing angle of these thyristors, you can vary the RMS value of the output voltage. And here, this is a three-phase AC voltage control. There are three phases, A, B, C or RYB, in which each phase there are two thyristors. They are connected back to back like a T1, T3, T5, T2, T4, T6. It is numbered like that one. And the firing sequence is T1, T2, T3, T4, T5, T6, T1, etc. So this is a topology of a three-phase AC voltage controller. In each phase, there are two thyristors back-to-back connected. This is a single-phase AC voltage controllers. And in each case, each can be again subdivided into, that is based here, unidirectional or half-wave control, bidirectional or full-wave control. Now, this is a bidirectional because we are using two thyristors in this phase. Now, instead of this thyristor, second thyristor, if you are using a diode here, positive half you have a control, that is using this thyristor T1. But instead of this thyristor, you are using a diode, that is called a unidirectional or half-wave control. In that case, unidirectional half-wave control will be replacing the thyristor by a diode. But a bidirectional full-wave controller will be using two thyristors. Here also is a bidirectional one. Because if you are using two thyristors, they are connected in back-to-back. Positive half cycle we can control by this thyristor T1, and negative half cycle we can control by thyristor T2. For both half can be controlled. That is why it is called bidirectional or full-wave controller. This is a bidirectional full-wave controller. And if you replace this thyristor by a diode, it is a unidirectional half-wave controller. Therefore, this is a single-phase AC voltage controller, which is a bidirectional one. And due to the line or natural commutation, here we are using the line or natural commutation for this thyristor, because there is no need of extra commutation circuitry, and it is very simple. Since there is already, it is crossing the 0 point where the current through the SCR is going less than the holding current, that device gets turned off. That's called the natural commutation is there. Therefore, no forced commutation is, or there is no commutation circuit is required. That is the advantage of this particular control method as such. For due to the line or natural commutation, there is no need of extra commutation circuitry, and it is very simple. Same circuit is shown here. Two thyristors T1 and T2, they are connected in back to back, and this is the load connected. This is the source as such. Now continuing the AC voltage controllers, of course I'm considering first single phase case. In a single phase system, if two thyristor switches or track, they are connected back to back between the AC supply and load, the power flow can be controlled by varying the RMS value of the voltage applied to the load. And this type of power circuit is known as AC voltage controllers. That is, here there is a single phase AC input voltage is there. Here the load is connected. You want to vary the RMS value of this voltage that is applied to the load. That can be done by either by connecting two thyristors that are anti-parallel, or by using a triac. Triac can also be used. For the most common application of the AC voltage controller is the industrial heating. It is widely using, or tap changing of the transformers, transformer connections, and light control. Lighting control is used, and speed control of polyphase induction motors. There are applications for AC controllers in which the input voltage is a fixed AC, but output voltage is a variable AC. The RMS value of the output voltage can be varied. Therefore, can use either two thyristor in back to back, or triac there can be used. During the positive half cycle, T1 is being controlled, and during the negative half cycle, T2 is being controlled. In this circuit, during the positive half cycle, T1 can be controlled, and if you replace this diode, this thyristor by a diode, there won't be any control on the negative half cycle. That is, in a unidirectional AC voltage controllers, this thyristor T2 will be replaced by a diode, so that you can have a control only in the positive half cycle. Negative half cycle, we will be using an uncontrolled diode. That will be explained in the coming slides. Another point is that here the gating signal to be given T1, that is, you have to gating signal between the gate of T1 with respect to its cathode. Similarly, gating T2 with respect to its cathode. In this case, the cathode, they are not common. This is the cathode terminal of the T1, and this is the cathode terminal of T2. The cathode terminals are not common. In that case, the gating circuit that is to be isolated. You have to isolate this gating circuit or gating signals to T1 and T2, since the cathodes are not common. But in this case, if you change the topology little bit like this one, you can see that when the two thyristors, they are connected in this fashion, the same cathodes are shorted, and there are two diodes, they are connected like this one, and this is also AC voltage controller in which there are four devices are using two diodes and two thyristors. But in this case, the cathode is common, terminal is there. Therefore, there is no isolation required between the gating signal of both these thyristors T1 and T2, because since we are giving the same terminal as the cathode, therefore it provides a common cathode connection for the simplifying the gating circuit without the need of isolation. No need of isolation is required in this case, unlike the previous circuit. Here both cathodes are shorted, therefore you can apply the gating signal with respect to this point. Similarly, gating signal with respect to this cathode is common. So no isolation is required in this case. Another change of topology, same thing is that instead of using, here two thyristors, that is only single thyristor is using. Therefore here a T1 is there, but there are four diodes are uncontrolled devices. Diodes are using D1, D2, D3, D4 are using here. Therefore, during the positive half cycle, we can see that here, as I explained, it seems no positive half cycle. This is the path. During the positive, this thyristor is conducting through this diode, it is returning back. And during the negative half cycle, again, it is through this SCR, through the diode, it is returning back. It is working. But in this case, during the positive half cycle, through this diode, say D1, then T1, and then here D3, and is returning back. During the negative half cycle of the input source, here it is coming here, it is D2, and through this again, same thyristor T1, and it is D4, and it's returning back. Therefore, in this case, you can see that only one thyristor is using. Here, two thyristors are using, but here using four, diodes are using. Therefore, one SCR and 4 diodes are that to reduce the device cost. Device cost will be reduced because rather than using 2 SCR, only 1 SCR, of course, 4 diodes are using because the number of devices now increased here to 5. Here it is 4. Therefore, the conduction loss will be more in this case. For this is another topology. Both that can be used for AC to AC converter or single phase AC controllers, voltage controller. There is no isolation is required for the gating circuit in both cases. Now continuing the AC to AC voltage controller as such, here single phase AC input voltage, here is a variable output voltage, RMS value output voltage. Now as I explained in the previous slide here, if you replace one thyristor by a diode like that one, let's say positive half cycle, this thyristor will be being controlled. Negative half cycle, there's no control. This is an uncontrolled device, diode is there. And this combination of a thyristor with a diode like that is sometimes called as thyroid, it is called. An SCR and a diode combination known as a thyroid controller. This is a thyroid controller in which the T1 can control the positive half cycle. This is the input voltage. By controlling the firing angle, by giving the switching gating pulses here, the positive half cycle we can have control this T1. But there's no control over the negative half cycle. Negative half cycle because we are using a diode here. For the half wave AC voltage controller, which is only one half it can control, negative half it cannot control. That provides a unidirectional half wave asymmetrical voltage control with device economy, but introduces, because one thyristor is replaced by a diode, as far as economical wise it is good, but the problem is that there should be DC component will be introduced, because you can see that one here, this is the output voltage waveform, positive half cycle this much voltage, positive voltage is across the load, this is a negative voltage. If you take the average value or you take the summation of this area, you can say net negative value comes, or you can see that one a DC value will be there. Similarly, harmonics also will be there. Therefore, the DC component and the more harmonics, thus this is not very practical to use except for a very low power heating load. Therefore, this type of circuitry or this type of topology is not widely using because that introduces a DC component as well as harmonics. Now continuing the AC voltage controllers. Now let us see the control methods as such. There are two types of controllers are generally used. Two control methods are using for this control. Two control methods actually. One we call it as on-off control. That's also called integral cycle control. Second control method is called phase angle control. And in this presentation, we'll be concentrating on the on-off control or integral cycle control. Now coming to the on-off or integral cycle control, this is a circuitry same. That is circuit topology, there's no difference. There's a input AC voltage is there. There's a load is there. There's a two SCRs are T1 and T2. They are connected back to back. And here, for certain number of cycles, load is being connected to the source. Full cycles. For example, in this case, three cycles, the source is being connected to the load. And the remaining few number of cycles, in this case 2 it is shown, 2 cycles here, load is being disconnected from the source. Therefore here we can see that this is the output voltage. In this case 3 number of cycles the load is connected to the source, or we can get load voltage is same as the source voltage. And for remaining 2 cycles this is disconnected, or the load is disconnected from the source, that is output voltage equal to 0. Then that is repeated. Therefore, this is the output voltage and this is the input voltage, and these are the gating signals. Gating signals to T1 is given the top one, and the gating signal to T2 is the bottom one. And you can see that the gating signal is given at the firing angle alpha equal to 0 for the positive half cycle. For the negative half cycle, again the firing angle alpha for the T2 it is given. Therefore, here the firing angle is alpha at 0. At the 0 crossing point, the firing signal is given. Therefore, these are the gating pulse to the T1 and these are the gating pulse to the T2. Therefore, when gating pulses are given to the corresponding SCR, that will be conducting so that the output voltage will be same as the input voltage. And that is why for 3 cycles in this case, the output voltage is same as the input voltage. And for the remaining 2 cycles, no switching signal is, so no gating pulse is given. No gating pulse is given so that the load is being disconnected from the source, output voltage equal to 0. Therefore, that is repeated. That means that certain number of cycles of the input load is being connected to the source, and certain number of the cycles of the input the load is disconnected. In this case, full cycle is being there. That is in on-off control, thyristor switches connect to the AC source to the load for a few cycle of input voltage, and then it is disconnected it for another few cycles. One thing to be noted that with the full cycles, not partial cycle, full cycle it is taken. But with the full cycle of the input voltage, it is connected, and remaining full cycle it is disconnected. Therefore, the number of cycle it is being connected is taken as, in this case, n, and number of cycle it is disconnected it is taken as m. And there's a term what we call it that duty cycle as such. Duty cycle means like a number of cycles it is connected, n divided by total number of cycles, n plus m. That ratio we call it as duty cycle. It is something like similar to the DC step down chopper. We have that certain time which is T on divided by total T on plus T off is called the duty ratio. It is like that one. Certain number of cycles of the input it is being connected, that is n, and certain number of cycles it is disconnected, that is m. Therefore, n divided by n plus 1 is called the duty cycle. Therefore, that is the case of a on-off or integral cycle control. In another one, that is in phase angle control of thyristor, same circuit topology, there's no difference, but firing angle is being controlled in each phase. For example, T1 is controlled by this changing the firing angle. T1 is, when it is on, you will be getting the output voltage same as the input. But once it is reaches the zero crossing point, that is this, the holding current it goes to holding less than holding current, that gets switched off. Then until the next firing, that is here pi plus alpha. This is pi plus alpha. This is being fired. Then you'll be getting a negative voltage same as the input voltage here. Therefore, the firing angle is being controlled. That's called the phase angle of this being controlled. Therefore, this is the input voltage and this is the output voltage, and that voltage divided by the resistance of the load, they will be giving the output current. Of course, this is the thyristor voltage is marked here. This is the thyristor voltage for the T1, and this is the voltage across the thyristor T2. So for this is a phase angle control, and we'll be discussing this in the next presentation. In this presentation, we'll be concentrating the first one, on-off control or integral cycle control. By doing the on-off or integral cycle control, we can vary the RMS value of the output voltage across the load. That we'll be seeing in the coming slides. Now coming to again the on-off control or integral cycle control. In AC voltage controller using on-off control, the thyristor acts as a switch connecting the load to the AC source for a few cycles and then disconnecting it for another few cycles. Therefore, in this case, this acting as a switch here for certain number of full cycle, in this case full cycle I'm telling, here 3, in this one 3 cycles, these are the load is being connected to the source. That is why you will be getting the output voltage same as the input voltage. The remaining 2 cycles, in this case, it is disconnected. The load is being disconnected. In that case, you are not giving any gating signal to either T1 or T2, so that the load is being disconnected from the source. Output voltage equal to 0. Therefore, then again it is repeated. Therefore, this is the output voltage and this is the input voltage, and this is the gating pulse to the T1 and this is the gating pulse to the T2. Again, the gating pulse is given at the zero crossing point. Firing angle equal to 0. Therefore, full cycle you will be getting. Therefore, the number of cycle it is being connected, that is represented as n. The number of cycle it is disconnected is m. N divided by m plus n, that is called the duty cycle. Continuing the integral cycle control or on-off control, and the circuit diagram is as already we have seen, a single phase input, and this is the load, and there's a 2 thyristors, they are connected back to back, T1 and T2, and the certain number of cycles it is being connected, load is being connected to the source, certain number of cycles it is disconnected, and here you have to calculate, this is the output voltage, what is the RMS value of the output voltage, how can it be related to the duty cycle. Now, for n number of cycles, it is on. That is, in this case, for n number of cycles, the load is being connected to the source. And for the remaining m number of cycles, it is off. Load is being disconnected from the source. For the total n in each, if you take each cycle of the input, it is equal to 2 pi radian. It is a 2 pi radian. Therefore, here, each cycle, the periodicity can be written as n plus m into 2 pi radians. Because each cycle 2 pi radian, there are such n cycles. Here on m cycle it is off. For the total periodicity is given by n plus m into 2 pi. N plus m into 2 pi radians are periodicity. And the RMS value of the output voltage can be calculated as it is equal to RMS value of it is equal to under square root, that is square root of integral 0 to 2 pi 0 to 2 pi each one, I'm telling 0 to 2 pi Vm square sin square omega t, square of that one. Root means square, it is square and it is integrated, and there are such n cycles are there, that is multiplied by n, and that is to be divided over n plus m into 2 pi. Therefore n plus m into 2 pi, therefore all are under square root. Therefore RMS value of the output voltage equal to under square root n divided by 2 pi into n plus m integrate 0 to 2 pi Vm square sin omega t d omega t. Now again n Vm square divided by, it is equal to sin square omega t, I can write as 1 minus cos 2 omega t divided by 2, or it is equal to n Vm square divided by 4 pi into n plus m integral 0 to 2 pi 1 minus cos 2 omega t d omega t under square root, or n into Vm square divided by 4 pi into n plus m. If you integrate this one, it is equal to omega t minus sin 2 omega t divided by 2. Limits are 0 to 2 pi. And substituting this limit, we'll be getting it is equal to n Vm square divided by 4 pi into n plus 1 into 2 pi under square root. And this is equal to, if you take outside square root, it is equal to Vm divided by root 2 into square root of n divided by n plus m, or n divided by n plus 1, as I told you, it is called duty cycle. Therefore duty cycle of the voltage controller, which is equal to k, which is equal to n divided by n plus m. N number of cycles the load is being connected to the source, and m number of cycle the load is disconnected from the source. For n divided by n plus m, that is called the duty cycle of the AC controllers, that is represented as small k, and the RMS value of this AC output voltage is given by, which is equal to Vm by root 2 into root k, where Vm is the maximum value of the input voltage, and Vm by root 2 is called the RMS value of the input voltage. Therefore, the RMS value of the input voltage into square root of k, this duty cycle, that is the RMS value of the output voltage. Therefore, the RMS value of the output voltage is given by Vs into root k, where Vs is the RMS value of the source voltage, and k is equal to the ratio duty cycle n divided by n plus m. Now continuing the on-off control or integral cycle control here, RMS value already derived. The RMS value of this output voltage, RMS value of this output voltage is given by Vs into root k. Vs is the RMS value of the input voltage, that is RMS value of the input voltage, which is equal to Vs, which is equal to root 2 times Vm. That into root k. Root k is the n divided by k equal to n divided by n plus m. That is number of cycles for which it is being connected, that is n, and this is equal to m. N plus m, n divided by n plus m is the duty cycle, which is equal to k. For Vs into root k equal to the RMS value of the AC output voltage. Now the RMS value of the load current is given by RMS value of the voltage divided by load resistance. I'm considering a load resistance R, which is equal to Vs into root k divided by R. That is the RMS value of the load current. One thing is that RMS value of the load current is same as the source current. Load current is same as the source current. That is why the RMS value of the source current is same as the RMS value of the load current. Therefore, RMS value of the input current or source current is same as the RMS value of the load current, which is equal to V0 divided by V0 R divided by R, or Vs root k divided by R. That is the RMS value of the source current. Another one is that what is the power delivered to the load? How much is the power delivered to the load? Because this is active power, we call it as. What is the real power consumed by the load? Power delivered to the load is given by what is the RMS value of the voltage square, that is V0 R square divided by the resistance V square by R. That is called the power delivered to the load. V0 R square divided by R, which is equal to Vs into root k whole square. Vs into root k whole square divided by R, or we can say that k into Vs square divided by R. Therefore, this is the power delivered to the load. Power delivered to the load is given by k into Vs square divided by R, where k is the duty cycle n divided by n plus m, and Vs is the RMS value of the input voltage. Therefore, k into Vs square divided by R is the power consumed or delivered to the load. Therefore, that's the active power. And the current at the input side is equal to the same as the load current, RMS value of the load current I0R, which is given by Vs into root K divided by R. Vs divided. Therefore, in this case, now to find out the power factor, what is the power factor the input side is given by what is the power consumed by the load, that is the active power divided by the apparent power. Active power means what is the power consumed by the load is equal to K into Vs squared divided by R. And apparent power is given by what is the RMS value of the source voltage into the RMS value of the source current. RMS value of the source voltage is Vs. And RMS value of the source current is given by same as RMS value of the load current, which is equal to Vs into root K divided by R. Therefore, it is equal to Vs into VO or Vs into root K divided by R. Therefore, it is equal to Vs K, root K into Vs squared divided by R. So, this is the apparent power, that is input VA, and this is the active power. KV squared by R is the active power, and the ratio of the active power to the apparent power VA, that is KW divided by KVA or VA. That ratio is called the input power factor. That is why it is equal to KVA squared divided by R divided by root KVA squared divided by R, or you'll be getting it's equal to root K. Or the input power factor for a on-off control or integral cycle control, the power factor at the input side is equal to square root of K, square root of duty cycle, or root of N divided by N plus M. Therefore, as duty cycle changes, the input power factor changes. Now continuing the integral cycle control or on-off control here, the input power factor we have seen it is equal to square root of K. K equal to duty cycle, which is equal to N divided by N plus M. That is the duty cycle. For as K changes, the power factor changes. As an example, in this case, then you can plot it that. That is the power factor versus the duty cycle is plotted here. That is, it's not linear. It is square root of K. Therefore, this is the plot of power factor versus the duty cycle K. Therefore, we can, as an example, we can see that one. If N equal to 50, the number of cycles for which the load is being connected to the source equal to 50 cycles, and if that is disconnected for 50 cycles M, then the duty cycle is given by N divided by N plus M, or 50 divided by 50 plus 50, or that is given by 0.5. 50 divided by 100 or 0.5, or duty cycle is equal to 0.5 with N equal to 50 cycle and M equal to 50 cycle. Then corresponding to that one, it is equal to the input power factor equal to square root of K. Square root of 0.5 means 0.707. Or as an example here, corresponding to a duty cycle of 0.5, the power factor is equal to 0.707. Therefore, as the duty cycle changes, the power factor will be changing in a non-linear fashion, which is equal to square root of K. And we can see that one, if the as the N or the N and M changes, the number of cycles for which the load is being connected and the number of cycles for it is being disconnected, that will decide the input power factor. So input power factor equal to square root of K. Now continuing the integral cycle control or on-off control, here each thyristor conducts for pi radians during the each half cycle on the one cycle. That is, for each half of the input cycle, 0 to pi radian T1 is conducting, pi to 2 pi radian T2 is conducting, again T1 is conducting, T2 is conducting. Therefore, the average value of the current through a thyristor, that is average value of the thyristor, can be calculated integral 0 to pi Im sin omega t d omega t, that is integrated, and there are such n cycles are there. For n cycles is being connected to the load. Therefore, there are such n cycles are there. It is connecting, that is this device is conducting, and that is to be divided over 2 pi into n plus m. Therefore, that is the average value. Therefore, n divided by 2 pi into n plus m, integral 0 to pi Im sin omega t d omega t is the average value of the current through the each thyristor, which is equal to Im by pi into n into m plus n, or will be getting, it is equal to, when you are calculating, it will be getting k into Im divided by pi. Therefore, k into Im divided by pi is the average value of the current through the thyristor. Similarly, we can calculate what is the RMS value of the thyristor current, which is equal to under square root n divided by, that is integrating between 0 to pi Im square sin square omega t square of, that is integrated, and that is mean is taken, that is there are such n cycles, n divided by 2 pi into n plus m, and all under square root. Therefore, root mean square value can be calculated. Root RMS value of the current through each thyristor, which is equal to Im by 2 into root of n divided by m plus n, or that is equal to, which is equal to Im into root k divided by 2. Therefore, that is the RMS value of the current through each thyristor, and this is the average value of the current through the each thyristor in on-off control or integral cycle control. Now, coming to the various observation of this on-off control or integral cycle control, let us see that the power factor and the power factor and output voltage vary with the square root of the duty cycle. Both power factor as well as the output voltage is varying at the square root of duty cycle, and the power factor is poor at the low value of the duty cycle. Thus, in integral cycle control of AC controllers, we can see that RMS value of the output voltage is equal to Vs into root K. It is varying as the duty square root of the duty cycle. Similarly, the input power factor also equal to square root of K. That is K equal to the duty cycle, which is equal to N divided by N plus M. So that's why power factor and the output voltage, this is the output voltage RMS value, that vary with the square root of the duty cycle, and the power factor is poor at the low value of the duty cycle. If the K value is very low, the power factor will be low. Therefore, another point is that if T is the period of the input voltage, the total, if there are M cycles of N cycle on, the total M plus N into T is the period of the on-off control, and this T plus N into T into M plus N should be less than the mechanical or thermal time constant of the load. That is a condition to be satisfied. Another point is that the sum of M and N is generally selected as 100. That is another observation. The sum of the number of cycles for which the load is being connected to the source, that is N, and the number of cycles what is being disconnected, that is M. M plus N is normally selected as in the 100. Therefore, these are certain observations of the on-off control or integral cycle control of a AC controllers.